Have you ever just stopped and thought about everything? The sheer chaos of it all? From the galaxy spinning in space to a single thought firing in your brain. What if I told you all of that complexity might boil down to just a handful of beautiful, simple equations? Well, that's exactly what we're going to explore. We're on a quest to find the code of reality itself.
You know, the great physicist Paul Dirac once said something really profound. He believed that the universe is written in the language of mathematics, and that this language is beautiful. Not beautiful like a painting, but a kind of deep, universal beauty that's the same for everyone, everywhere. And that's our theme today. We're looking for that elegance, that simplicity, that unity in the laws of nature. So that brings us to the big one, right? The question that's kept physicists up at night for centuries. Is it even possible? Can a few lines of math truly explain our entire messy, wonderful reality? It sounds a little crazy, but let's dive in and see how close we've come.
All right, to start this journey, we've got to go way back. We're talking the 1600s. This is when scientists first started to write down the rules of the game, so to speak. And they began by looking at two forces that, on the surface, seem to have nothing to do with each other.
First up, you've got the big one, Newton's law of universal gravitation. This is the classic, right? The apple falling from a tree story. But what's so amazing is that this one simple rule explains both that falling apple and the moon circling the Earth. It's all about how much stuff, how much mass an object has, and how far apart things are. Okay, now fast forward about 100 years. A new player enters the game, Coulomb's law. This one isn't about mass, it's about electric charge. It describes the push and pull between tiny particles. And just like gravity, its strength depends on a property of the object, its charge. And, you guessed it, the distance between them. Are you starting to see a pattern emerge? Because physicists sure did. And this is where things get really, really cool. Just look at the math here. They're practically twins. Both gravity and the electric force follow this inverse square law. That just means that as you double the distance, the force gets 4 times weaker. It's the exact same relationship. The universe was using the same blueprint for two totally different things.
Yeah, there was no way this was a coincidence. For physicists, this was like finding a Rosetta Stone. It was a giant, blinking neon sign hinting that maybe, just maybe, these forces were secretly related. It's like that great quote says, as if the same algorithm was used for both. And that clue, that beautiful bit of shared mathematical DNA, kicked off one of the first and honestly one of the most successful unifications in the entire history of physics.
So step into the 1860s. A genius named James Clerk Maxwell comes along. He sees all these scattered ideas about electricity and magnetism, and he does something incredible. He gathers them all up and weaves them together into just 4 elegant equations. And when you put these equations together, something magical happens. They revealed this beautiful dance. A changing electric field actually creates a magnetic field. And guess what? A changing magnetic field creates an electric field. They weren't separate things at all. They were just two faces of a single unified force, electromagnetism.
But wait, it gets even better. This is the grand finale. When Maxwell combined his laws, an entirely new equation just popped out, the wave equation. And it predicted that these back-and-forth electric and magnetic fields would travel through space as a wave. And when he calculated the speed of that wave, it was the speed of light. I mean, can you imagine that moment? He had just explained what light is. It's just a ripple in the electromagnetic field. Absolutely mind-blowing.
Okay, so seeing that kind of unification makes you wonder, right? Is this just a happy accident, or is there something deeper going on? Is there a fundamental reason why the laws of physics are so elegant and interconnected? A kind of rule behind the rules. To get to that answer, we have to look at the world in a completely new way. For centuries, physics was all about forces, pushes, and pulls. But a new way of thinking came along called Lagrangian mechanics. And it said, forget forces, let's look at everything in terms of energy. And by looking through this new lens, a massive secret about the universe was about to be revealed. And that secret has a name. Noether's theorem. Honestly, this might be one of the most beautiful and powerful ideas ever conceived. Here's the core of it. For every symmetry you find in the laws of nature, there is a corresponding quantity that is always conserved. No exceptions. A symmetry just means you can change something like your location or your orientation, and the laws of physics don't change one bit. Let me give you some concrete examples, because this is huge. Why is energy always conserved? Why can't we create or destroy it? Noether's theorem tells us it's because the laws of physics are the same today as they were yesterday and as they will be tomorrow. They have time symmetry. And what about momentum? Why does a moving object keep moving? Because the laws of physics are the same here as they are on the other side of the galaxy. Translational symmetry. Suddenly, these fundamental conservation laws weren't just random rules. They were the direct consequence of the universe's beautiful symmetries.
Okay, so this powerful idea, this search for unity and symmetry, was the rocket fuel for the 20th century. It led to the two greatest theories in all of science. But here's the crazy part. In their incredible success, these two theories also created a massive, gaping chasm right in the heart of physics. It's like our picture of reality split right down the middle. We ended up with two different instruction manuals for the universe. One describes the big stuff, planets, stars, galaxies, the whole cosmic dance, and the other describes the tiny stuff, the bizarre, fuzzy world of atoms and subatomic particles. And these two instruction manuals don't just disagree, they are fundamentally at odds with each other. Einstein's general relativity, our theory for the big stuff, sees space-time as a smooth, flowing, continuous fabric. But quantum mechanics, our theory for the small stuff, sees a universe that's chunky, pixelated, and ruled by the strange laws of probability and uncertainty. One is like a gentle, curving hill, the other is like a staircase made of Lego bricks. They just don't fit. And this is the central conflict of modern physics. The math of one theory completely falls apart when you try to apply it to the other's domain. When you try to zoom in and describe gravity on the tiny scales of quantum mechanics, the equations just spit out gibberish, infinities. It's a total breakdown. So the force we know best, gravity, has no place in our most precise theory of reality, the standard model of particle physics. That right there, that's the biggest puzzle in all of science. So where does that leave us? Is physics broken? Did we hit a dead end? Absolutely not. In fact, it's the opposite. You see, in science, a big contradiction like this isn't a failure, it's a signpost. It's pointing the way to an even deeper truth. This massive incompatibility is actually the driving force, the primary motivation behind the search for the next great unification. A single theory of quantum gravity, what some people call a theory of everything. And what would a theory like that do? Well, it would be the ultimate unifier. It would bridge the gap between the world of the cosmos and the world of the quantum. It would give us the tools to finally understand the most extreme places in the universe, like what's really going on at the heart of a black hole, or what happened in the very first fraction of a second after the Big Bang. These are the places where both gravity and quantum mechanics are in full effect, and where our current theories just give up. This is it. This is the absolute frontier of human knowledge, the hunt for that single, beautiful piece of code that underlies all of reality. And it leaves us with one final epic question. Will we ever find it? Will we reach the end of the story and read that final equation? Or is the universe's code infinitely complex, a book with no last page? We don't know the answer, but the search is what drives us forward.